Welcome back. So we will carry on with the Euler-Lagrange. As one thing I need to do is to decide how far I can go so that people see me or see this blackboard. I think I can go as far as here and perhaps here. Right. Just a recap. We're looking at the problem of extremizing the functional f of y given by an integral between alpha and beta of some given integrand little f of x, y, and y prime dx. And the way we proceeded, so y here is a function of x, such that the endpoints of the graph of these functions are fixed. So y of alpha is y1, y of beta is y2. And the way we proceeded is we assumed that there is a solution to this extremization problem. And we've perturbed this solution, and we looked at the way the functional changes to the first order, and for the critical point in the function space, it should not change at all. And that gave us a condition, which I call Euler-Lagrange equation, which is a necessary condition for y of x to be a critical point.
Okay. Can we start writing by df?
I beg your pardon?
We start writing from df.
From what?
df and down. Not because
from dx.
Yeah.
Fine.
Okay.
And this condition, you see, was this: df by dy minus total derivative with respect to x, df by dy prime equals 0, and that's the key equation for this part. Because I think we numbered it. This was 2.3, and this is our Euler Lagrange equation. And it's a it's a boundary value problem, a second order equation where we have y fixed at two endpoints, and it can often be an easy in applications and linear differential equations hard to solve. And I said that a way to try to solve it explicitly is to look at first integrals. So you have situations where this equation can be integrated once to a first order ODE. And I've demonstrated one such situation, and that was where f didn't explicitly depend on y. And by looking at this case, we were able to find geodesics on the plane. And I think I called this case A. So did I call it case A or was it case 1?
Case 1.
Okay, so now I look at case 2, another occurrence of first integrals. First integrals. Case 2. And so we're going to assume here that the integrand in the functional doesn't explicitly depend on x. It will depend on x via y and y prime, but not explicitly. But even, well, perhaps before I do that, let me motivate this assumption by the following calculation. I'm sorry, Hiba has warned me I should do this. So I say calculate. I'm going to calculate the derivative, total derivative with respect to x of the following quantity: f minus y prime df by dy prime. And well, we will see, we will in this calculation use the Euler-Lagrange equations, and we will see that this derivative is under certain circumstances can be 0, in which case the bracket has to be a constant. So let's see when that happens. Well, first term is the total derivative of f with respect to x. Remember, we need to use the chain rule. So this is df by d little x plus y prime df by dy plus y double prime df by dy prime. So I explained yesterday how this comes about from applying the chain rule to d by dx. Then d by dx hits this term. Okay, so now I'm using the product rule. The first term I need to differentiate is y prime, but its derivative is y double prime. So I have minus y double prime df by dy prime. And then I need to differentiate this. So I write minus y prime d by dx df by dy prime. Okay, so what happens now is there is a one cancellation. These two terms cancel. And I found that the whole thing is equal to df by dx partial. And I group these two terms together. So I have plus y prime df by dy minus d by dx df by dy prime. Now, you see, we are assuming here that y is a solution to the Euler-Lagrange equations, and here we recognize the Euler-Lagrange equations in this bracket. So this term is 0 by 2.3, and I'm just left with df by dx. Now, if little f doesn't explicitly depend on x, then the whole thing is just 0. Okay, but then we've discovered another first integral, because if this derivative is 0, then the term in the bracket has to be a constant. But this expression is a first, this expression equals a constant is a first order ODE for y rather than a second. So if df by dx equals 0, first this means no explicit x dependence in f, then f minus y prime df by dy prime equals a constant. With a number. Now, I think this would be 2.5. Can you please look at my last number of the equation? Yes, 2.5. This first integral up to an overall sign is in theoretical mathematical physics context referred to as the energy. And I'll maybe have more to say about it later. So if you were to apply this procedure to this function f, where f is a Lagrangian for some mechanical system, then you will discover that in case potential in this mechanical system doesn't explicitly depend on time, the constancy of this expression is precisely, if you invert the overall sign, is precisely equivalent to the constancy of the total energy of the system. So I just write in inverted commas the energy. Although our considerations go beyond. Right, so now with this integral in mind, I'm going to go back to our first motivating problem for the subject, the one I told you about a week ago online. The problem posed by Bernoulli, the brachistochrone problem. If you look back at your notes, and if you don't have them, I'm going to write the functional down on the board again. There, the brachistochrone problem was reduced to axiomizing certain functional, which involved y prime, but didn't have any explicit x dependence. So we precisely, in good shape to try to apply this to that problem and hopefully solve the brachistochrone problem. Let's see how this blackboard is going. It's actually, it's failed. This is okay. Hi guys on the back to brachistochrone. Remember that the problem there is following. We on the xy plane, like we had 2 points, and one of them was chosen to be the origin, and the other one was chosen anywhere, so negative values of y. And we are considered possible shapes of wires connecting these 2 points, and the objective there was to find the shape of a wire for which the travel time of a particle moving on this wire, starting from rest under the influence of gravity, is the smallest. So we don't know what this shape is, but here maybe it looks like that. And it's better than any other possibility. And that led us, so I derived this in my first lecture, that led us to the following functional. F of y was an integral, well, this time what I called alpha, which is a smaller value of x is 0, to beta, and I had 1 plus y prime squared divided by minus square root of y dx. And that was the brachistochrone, and it's a square root of minus y because the way I set it up, the position of the point B corresponds to a negative value of y. Right, so now this is this here is our little f, and this little f only depends on y and y prime explicitly. So df by dx equals 0, and we're going to apply 2.5. Let's see if I gave some name to the constant there. Okay, so let's rewrite 2.5. I have square root of 1 plus y prime squared divided by minus y minus y prime times the derivative of this with respect to y prime. So that is y prime divided by square root of minus y root of 1 plus y prime squared, and that equals constant. Okay, so now let's calculate with it and try not to make a mistake. I'm going to put this at the common denominator. So I'm going to multiply the numerator and the denominator of this expression by a square root of 1 plus y prime squared. So now I have my denominator, which is minus y 1 plus y prime squared. And what do I have in the numerator? Well, I have this squared, which is 1 plus y prime squared, minus y prime squared, and that equals k. So now these two terms cancel. I can multiply both sides by the denominator and square them, well, maybe only by this part of the denominator squared. So if I do that, I have y minus y 1 over minus k squared y. So I divide by that. I square and I divide by k squared. And that equals to 1 plus y prime squared. And that is looking good. I mean, why is it looking good? Because it's the first order ODE. We already see one constant of integration, this k, and it's separable. So I need to separate it and integrate it. It's a big change of variables for it, which I've which we can all work out. So if you separate it and integrate it once, you get it to x equals plus or minus k integral of square root of minus y 1 plus k squared y dy. So the separation of variables gives you x as a function of y rather than just y as a function of x. Now this is still not an integral you can perform, but you see what we're interested in, and here's an interesting trick. We're interested in the shape of this curve. So what I'm going to do is choose certain parametrization of y, so the substitution, which will give me y in terms of some parameter, and then I'll be able to integrate it, and then x will become a function of this parameter. So that once that settles, I'll have what's called a parametrized curve, where both x and y depend on the parameter. And the substitution worked out is, in fact, I should say the following. I'm going to, at the end of this course, which will be tomorrow, by the end of this course, I will have produced an example sheet for you with problems, maybe 10 problems, and you can, you should solve these problems. And I've asked Professor Toma if there are any tutors or anyone who would be willing to mark this for you. I mean, I won't be able to do it myself, but I'll be, this would be, I can maybe provide some hints to these tutors. So you have, even if nobody marks it, have a go at solving these problems. And these problems will often be filling in odd ends calculations like this, and some rules. Okay, so the substitution is this. You take y to be minus 1 over k squared, sine squared theta over 2. Then from there, you calculate dy in terms of sine theta and d theta. You substitute it here and there. Well, you find that you can integrate it. So it will be one of these exercises. And the answer, the integral is plus or minus 1 over 2k squared theta minus sine theta plus c. Where c is another constant of integration. Then, if you impose the initial condition, that point A is 0, 0, so this curve goes through 0, 0, where theta equals 0, you find that C equals 0. Okay, so our final solution there is a parametrized curve given by x equals theta minus sine theta over 2k squared, and y equals minus 1 over k squared sine squared theta over 2. So this curve is parametrized by theta, and this is a parametric equation of a curve called the cycloid, which by different means was found by Bernoulli in 1697. So what's, a cycloid is an interesting curve in its own way. Cycloid is a curve which is traced by a fixed point on the circle when this circle rolls without slipping over a line. Let's have it up as we did before. And now let's imagine circle. And this circle will have a point, but this circle rolls, and when it does, the point rolls with it. And its trajectory looks sort of like that. Cycloids have cusps, so they have points of, which are not smooth. But for our histogram problem, we never reach this cusp because the shape of the wire will be somewhere between here and there. The curve traced by a point on a circle, if the circle rolls along a straight line. And if you have access to some computer programs or you like coding or not, you can take, if you haven't seen this before, take this parametrization of a cycloid and animate it where theta varies between maybe 0 and 4 pi, and then you will see how this shape comes up. Okay, so this was the second example of the Euler-Lagrange equation. Now, the title of this mini course is calculus of variations and geometry. I'm going to start steering it towards geometry. And the two bits I want to tell you about, well, will be minimal surfaces, so sometimes known as solar fields or salt bubbles, and also a bit more about the geodesics, but moving away from, from the Euclidean plane to some other surfaces. So let's do that. Now, before I do it, to present a slide to generalize. So these Euler-Lagrange equations, they can be generalized in many directions. Yes.
Corresponds to which angle on the graph that you want? It's the angle between the 0 and the point. So
The angle theta is the polar angle of a you know, if I were to think of my system, let me think about it. No, good. In terms of this mechanical analogy, this rolling analogy, the angle theta corresponds to the angle between the point on the circle and this fixed line on which it rolls.
and yes,
Yes. Okay. So how, you know, how and why would you want to generalize the Euler-Lagrange equations? Well, so our setup was we had one function of one variable. Now, so one dependent, if you like, and one independent variable in the Euler-Lagrange equation. Now, we could have many dependent variables and one independent variables. And this generalization, quite straightforward, would lead not to one Euler-Lagrange equation, but to a system of Euler-Lagrange equations. And that's the one we will need. But you know, the derivation is really identical to what I presented yesterday. Another generalization arises if you have one dependent variable, but many independent variables. And this is, I mean, it's interesting, but like I said, I'm going to skip that generalization. If you were to proceed in that direction, you would see that the Euler-Lagrange equation, the ODE, is replaced by a partial differential equation. So you can get things like the Laplace equation, or wave equation, or physicists, things like Maxwell equations and others from variational perspective as partial differential equations, not ordinary. But I'm not going to do it. Instead, I'll just say that generalize Euler-Lagrange to several dependent variables. Okay, so now I have a function y which maps R to Rn. So actually I don't know what's your, so when I grew up in Poland, the way we denoted vectors with an arrow on top of a letter. But when I moved to England, I found that the way they denote vectors is with a line underneath a letter. So what is that you do here?
Both, like in Poland.
Both?
No, like in Poland.
Like in Poland? Do you really?
Yeah.
So you do this?
Yes.
Okay. But then another notation you can use is you can refer to once the coordinate system has been fixed, you can refer to and think of this vector in terms of its components. So this vector y, its components y y1, and it's a function of some x, y2, it's a function of x, up to yn, function of x. And it's a function of x because it's map. So now we have a curve not in R2 but in Rn. So I'm going to have my Rn as 3-axis. And this curve can again join points. And let me not call the independent variable x. Let me call it t. I'm sorry. So along this curve, the vector y depends on t. Okay. Now we aim to extremize a function of f of this vector function, and that's an integral between some alpha and beta, because we'll be integrating over t. And I have little f of well, that depends on the independent variable, which is t, and that depends on the dependent variables y1 up to yn, and it depends on the first derivatives of these variables, y1 dot up to yn dot dt, where dot stands for d by dt. And the derivation, which I'm not going to repeat, proceeds the identical way to what we did yesterday. So we are assuming there is a solution. And look at perturbing this solution up to first order by some vector function eta t, such that eta of alpha equals eta of beta is zero vector. Applied this fundamental lemma of calculus of variations. And if we do all that, go to the derivation, we have we arrive at the system of n second order ODEs, called now Euler-Lagrange equations. And they are following df by dy I minus d by dt df by dy dot I equals 0. And here this index I goes between 1 and that. And this system of ODEs is complemented by boundary conditions. Y of alpha equals perhaps y1. Y1 is constant, and y of beta equals y2. Now, this is the system I'll be using in my geodesic considerations. But now, perhaps let me just give you one example, because I know Professor Thomas told me that many of you are physicists. let me now give you one example how this sort of system arises naturally in physics. So example from physics. I'm going to take m equals 3. So we now have a curve in 3 dimensions. And I'm going to take a special form, of f. I'll take f to be some constant m times y vector dot squared over 2 minus some function which I'm calling v, which depends only on y, but move the derivative. So it depends on y1, y2, y3. So it depends on y. And this, this is called the Lagrangian, and in mechanical terms, it's a difference between the kinetic energy and the potential energy. Okay, so let's now see, and the name one uses for this f is a Lagrangian. In fact, because I mean it's fair to say that a lot of these calculus geometry type considerations, which eventually led to pure mathematics, a lot of it was back in the day motivated by mechanical problems. One uses the term Lagrangian for the integrand in these functionals, even when one doesn't talk about mechanics. Okay, so the Euler-Lagrange equations involve this Lagrangian. Anyway, we have this Lagrangian difference between kinetic and potential energy, and we're writing down the Euler-Lagrange equations. Okay, so let's compute the first terms. df by dy I, well, the yi dependence only sits in the v's, so this is minus dv by dyi. Now df by dyi dots, well, that comes from here. And if I take a norm of the derivative of back to y, this is y1 dot squared plus y2 dot squared plus y3 dot squared. Differentiate the factor of 2 will cancel this 2. This is m y I dot. So our system, but now this, you see, I need to differentiate again with respect to t, move it to the right hand side. And our Euler-Lagrange system becomes my double prime I equals minus dv by dyi. But this we recognize nothing as Newton's equations for a particle moving in the potential v. So in terms of Newtonian terminology, the force in the Newton's equation is a conservative force. It arises from a potential, and as such, there is a conservation of energy. Now, what is there to be said about this example? You see, at some level, we've reformulated Newton's equations which precede variational principles in variational terms. So what are the advantages of doing that, if any? Well, you see, that depends on the perspective. If you're a mathematician interested in kind of formalism and its elegance, you will be aware, or you will notice that Newton's equations, as will be not invariant under arbitrary coordinate transformations. So Newton's equations in physics language, they valid only in certain frames, in inertial frames. And if you change the frame, you cannot just change the, make the transformation between positions and time in an arbitrary way so that Newton's equations follow. The Lagrange equations, on the other hand, are, I'm not showing this in this mini course, but Lagrange equations are invariant by general coordinate transformations. So there is a bigger symmetry group of the equations. And that, is good to have if you want to do your calculations in a coordinate independent way. If you're a philosophically minded person, then you could find the idea that nature minimizes something in the motion attractive. So and that was really picked by the this approach to Newton's equations is sometimes called the principle of least action, also known as the Maupericius principle. And if you think formulated in right terms or dressed appropriately, it says that there is this mystical quantity, the Lagrangian, which is this T minus B, and things in nature, in the universe, move in a way which make this functional minima. So the nature chooses the simplest path. And this is, to some extent, an attractive idea, especially because we now know that most, if not all, laws of physics can be formulated as a variational principle, as a principle of least action. As yet another advantage, if you pass from classical physics to quantum physics, there are procedures, there are not really procedures of quantizing Newton's equations, but there are beautiful procedures of quantizing Euler Lagrange equations. And one, as I said more than once, the problem we've solved at the moment was finding a trajectory between 2 points, A and B, which minimizes whatever functional we want to minimize. In our case, it's Lagrange. So that there is a formulation of quantum mechanics and something on from there, quantum field theory, which takes this as a starting point, but says that unless the classical particle moves on this trajectory. In the approach I'm telling you about, Feynman's path integral approach, the quantum particle takes all possible trajectories between A and B, but with different probabilities. And there is an ingenious way of summing over these trajectories, doing what's called the path integral, with different weights attached to these probabilities, and finding the right probability amplitude for a particle going from A to B. And this takes this Lagrangian approach as a start. But I could have pushed this in that direction, but I'm not going to do that. I'll move towards geometry. So today we have 2 lectures, and I think this is a good time to have a 10 minutes break. Okay, we reconvene sorry, I'm still on UK time. What time is it?
That's 4.
4. So we reconvene with 10 to 4. We meet at 4 again. Okay?
Yes.
Now we're having a 10 minutes break. Hello, I think there is one potential student attending online because I can see that there is Professor Tuma there. and center of advanced things, so that's Hiba, and one person who is there, so I'm going to comply with the regulations and move my line here as Hiba told. So we'll move to maybe new section and geometry. And calculus of variation. Right now, let's start with the geometry of a curve in our frame. Let's denote the coordinates in our frame by this time capital X, you'll see Y, capital Y, and capital Z. And along the curve, capital X depends on T, capital Y depends on T, and capital Z also depends on T. So it's a parametrized curve. How we are to find the length of this curve? Well, it's not as simple as computing the distance between A and B, because that would be a length of a segment. But for a curve, Pythagoras theorem holds infinitesimally. So if we take a very small segment on this curve, then the length of this segment is square length of this segment is dx squared plus dy squared plus dz squared. So that's ds squared, the squared line element. If I then substitute x, y, and z to be functions of t in this formula, then this term along the curve becomes x dot squared plus y dot squared plus z dot squared times dt squared. So the length of the curve of, let's call this curve gamma, length of gamma is an integral from t1 to t2. These are the values of the parameters corresponding to the end point and the start point of the curve, of where the square root of this line element, which is the square root of x dot squared plus y dot squared plus z dot squared dt. Okay? Well, that's how you calculate the length of a curve in space of any dimensions. And in fact, if we were to, and we've done it already on the surface, if we were to set up a variational problem which minimizes or extremizes this length, we would have found that the critical point corresponds to a straight line. Now, I want to consider curves not in R3, but curves on surfaces in R3. So I'll talk now about, let's keep that in mind, but forget about curves for a moment. Let's talk about surfaces. So we see, what is a curve really before I do that? A curve is a map from some interval of a real line or real line onto R3. so over an interval. I want to think of surfaces instead. Call my surface sigma, and it's a surface in R frame. There are other surfaces, and we'll talk about those too. Surfaces were not embedded in R frame, but let me start off with this. So still have our capital X, capital Y, and capital Z, and some surface. So this, think of a surface of a sphere, if you want to do it in X, Y, Z space. Now, the surface is parametrized, locally parametrized by two coordinates. So we can think of this surface as a map from some open set, open or even closed set U in R2 to R3. So sigma really maps U to R3. What this means concretely, and I want to have a concrete description, is on the surface, these coordinates capital X, capital Y, and capital Z are not independent, but they all functions of some two parameters. So let's say that these parameters, the coordinates on the surface, the coordinates on U, will be called little x and little y. The coordinates on U. And to define a surface, we need to construct capital X, which depends on little x and y. Capital Y, which depends on little x and y, and capital Z, which depends on little x and y. And that's called, this presentation of the surface is called a parametrization. So this is a parametrized surface. For example, if I take X to be cosine of little x, sine of little y, and I take y to be cosine of little x, cosine of little y, and I take z to be sine of little x, then what surface do you think it is? It's a sphere, because we can verify that for this parametrization, x squared plus y squared plus z squared minus 1 equals 0. So it's a unit sphere. This is another way to give a surface. So we can think of this as some function g of x, y, and z equals 0. Sometimes surface can be given like this. Sometimes the surface can be given like this. And sometimes, like in the case of a sphere, you can go between these two formulations easily, but often you cannot. And what I'm going to try to tell you about, it is this way of giving the surface which I'll prefer. Okay. Now, Let's see. So now I'm going to introduce a concept which in old-fashioned but correct 19th century geometry is called the first fundamental form, and nowadays it's called the Romanian Metro. And this arises as a Pythagoras theorem, this line element, if you like, restricted to the surface. So restrict bs squared, which I've defined in terms of capital X, capital Y, capital Z, to sigma. How do I do that? Well, I'll do it explicitly. So capital dx is, what I'm going to use, I hope it's okay, I'm going to use this subscript to denote partial derivatives. You happy with this notation?
Yes.
Yeah. Now, now I might even use this notation. So I'm going to have a vector R, which has components x, y, z. So what I'm computing, ds squared is dr dot dr. It's exactly what I had before, but I'm substituting this here. And what will happen? Well, I have this dx, and I have to square it. So there'll be a bit of little dx squared, and then there'll be a bit of little dx square of squaring dy, and a little of dx square from squaring dz. X squared plus yx squared plus zx squared, this times dx squared. And there'll be the cross terms plus 2 xy plus yx yy plus zx zy dx dy plus xy squared plus yy squared plus zy squared dy squared. Now, this looks complicated, but the point is, if we given this parametrization of the surface, like this or like this, then all these things in this bracket, so this one, that one, and this one, they are some known functions of little x and little y. So we can just write it, one does, as some e. And this e depends on x and y, dx squared, plus 2f, and this f depends on x and y, dx dy, plus g, and this g depends on x and y, dy squared. Okay, and this object, this 3.1, which is a quadratic form in these differentials, dx, dy, z, that's called the first fundamental form. Or it's also called Romanian Metro. Okay, such objects can be introduced in any dimensions, whether it's the quadratic forms in the derivatives. And in some older textbooks, when they talk about this first fundamental form, they, rather than writing these quadratic forms in the differentials, they'll talk about the matrix, a symmetric matrix with 2 by 2 matrix with coefficients E, G, F. That's another representation of the first fundamental. Okay? So this first fundamental form, the Riemannian metric, it's what's left from Pythagoras theorem if you restrict it to a surface. And same way we used Pythagoras theorem in R3 to compute length of curves, we're going to be using this first fundamental form on the surface to compute the length of curves on the surface. So now I can go back to this picture. Actually, we can, as a reality check, we can maybe, I'm going to confuse my little x and y. We can say what this first fundamental form is on the sphere. This first fundamental form is, by the way, usually called G, so I'm going to call it G. And for the sphere, the way I presented it here, on unit sphere, G is, we need to do the calculation from memory, which you find is the y squared dx squared plus sine squared x dy squared. So my, if I've done it right, then my x plays a role of theta, what you usually call theta, and my y plays a role of what you usually call phi. So, on the sphere, this cross term doesn't exist, it cancels. Now, on our surface, consider a curve. But this curve lies on the surface. I'm going to refer back to this picture. Curve gamma in sigma. So how do I think of this curve concretely? Well, before I thought of capital X, capital Y, and capital Z as functions of a parameter t. Now I'm going to think of little x and little y as functions of t. X equals x of t, y equals y. Okay. Now I'm going to compute the length of this curve on the surface. And well, I can think of this as a functional. I see. I've used this letter F because it's conventional to denote the coefficient of the matrix. I'm not going to use F for the functional. Instead, I'm going to use L. So this L is a functional of a curve, and this is an integral between the values of t corresponding to points A and B. So this one has T1 and this one has T2. Now, it's a two-step process, but we've taken the bigger step already. I'll take the Pythagoras theorem and think of capital X and capital Y and capital Z as a function of t. But really, because it's on the surface, I could have first thought of capital X, capital Y, capital Z as functions of little x, little y, little z. That gives me this. And I think of little x, little y, little x and little y as functions of t. And I need to take a square root of this, because this is the squared length element, and I want to take a square root and integrate. So I have square root of e x dot squared plus 2f x dot y dot plus g y dot squared dt. So this, I mean, this is the kind of moment where I would not want you to get lost. Do people see where this comes from? It's a line element, first restricted to the surface, and then restricted to the curve. And I've used, in going from here to there, I've used the formula like dx equals x dot dt, and dy equals y dot dt. And you see this and this, they go here, and I take the square root, and dt squared is square root. Right. Now, the objective now is to find, for 2 points on the surface, is to find a curve which minimizes the distance, if such curve exists, which minimizes the distance between these 2 points. But now we in good shape to do it, because you see, this is almost what I finished off with, half an hour. It's a functional with 2 dependent variables. These variables are x and y, and 1 independent variable, and these independent variables. So this is so now I can define what the geodesic equations are. Geodesic equations. Let me give this a number. This will be 3.2. They the Euler-Lagrange equations. With 2 dependent variables. Well, I called them y vector before, so the components are x and y, and 1 independent variable t for the functional 3.2, or Lagrangian, or functional Lagrangian. You see, every time even if somebody gives you a surface, if you can carry on this procedure and find out this Romanian metric, and that's algorithm for first fundamental form of the surface, you then arrive at this functional, and you write down the Euler-Lagrange equations for this functional. And when you do that, remember that E, F, and G depend on x and y. Then that will give you geodesics, if you can solve this. So let's look at one basic example. I mean, in this example, I'm going to take certain shortcut simplification to see exactly how that goes. In fact, I might tell you what this shortcut will be. I mean, that's how you can do it properly, parametrizing x and y by t. But you can also, on the surface, if you have a curve on the surface, you can choose to parametrize it by one of the coordinates. So you can say that if a surface has coordinates x and y, then a curve on this surface is y as a function of x, or maybe x as a function of y. Okay. So if you're, I mean, it's very basic, but I want to be crystal clear. So there is a difference between parametrized curve and unparametrized curve. If you look at maybe a line, straight line in R2 with x and y as coordinates, so R2 is also an example of a surface. And the Riemannian metric on R2 is just dx squared plus dy squared. Well, there are two ways to write a line. You can either write y equals mx plus c, or you can write x equals alpha t plus beta, y equals gamma t plus delta. This is the parametrized form, and this is the unparametrized form. Of course, if you have the parametrized form, then it's easy to go to the unparametrized form, because what you do is you maybe take the first equation, you solve it for t, you plug it into the second equation, and you group your constants alpha, beta, gamma, delta, so that you can see m and c. Okay? This appears to be containing more information than this, but that depends what you want to do with, with your curve. If all you're interested in is the shape of the curve, trajectory, then there is no loss of generality in using this instead of this. I mean, this will give you a straight line. If you're motivated by physics consideration, and you think of this straight line as a trajectory of a particle, and you want to calculate the velocity of this particle, then you want to differentiate with respect to t, then that's the form you want to have, because the velocity vector for this straight line is alpha gamma. Here there is no time to differentiate with respect, but physics analogy aside, I just want to stress the difference between parametrized and unparametrized curve. And our Lagrangian approach led us to parametrized curves. One can sometimes instead, it's convenient to do that, at the level of the Lagrangian, eliminate t and use either x and y as a parameter. So that's what I gave you this simple example, because that's what I'll do. That's what I'll do next. So go back to this sphere, unit 2 sphere in R3. Well, the first fundamental form there was dx squared plus sine square x dy squared. Okay? So let's read off what E, F, and G are. In this case, E equals 1. F equals 0. And G equals sine square of x. Maybe now, if I write E dx, well, so what I'm doing really is I'm calculating a square root of this. So I have a square root of dx squared plus sine squared of x dy. instead of thinking of x and y as functions of p as I did here, I can think of x as a function of y or y as a function of x, and parameterize my curve on the sphere line. So the choice, let's say that I think of y as a function of x, parameterize curve as y equals y of x. If I do that, then dy becomes y prime dx. Okay. And what happens with this? Well, this becomes 1 plus sine square x y prime squared dx. Okay. So now the problem of finding a geodesic on the sphere reduces to the problem of actually solving only one Euler-Lagrange equation. So minimizing length, which is now an integral between x1 and x2, two values of x in the sphere. X is this azimuthal angle, square root of 1 plus sine square x y prime squared dx. Yeah, but now we're really in the familiar territory, because we got there from geometric considerations, but now we have, sorry, it's unreadable. Let me write this again. Square root 1 plus sine square x y prime squared dx. That's our f. And we're in a familiar territory of solving an ordinary type of Euler-Lagrange equations. Moreover, there appears to be first integrals, right? Because our f explicitly depends on x and y prime. It doesn't depend on y. So I'm going to use the first integral, which I found last time. So Euler-Lagrange equations 2.3, simplify due to existence of first integral. First integral is df by dy prime equals constant. That's a constant if f doesn't have explicit y dependence. So what happens in our case? We need to differentiate it with respect to y prime. So if y prime divided by square root of 1 plus sine square of x y prime squared, and let's see. Okay, so let's tidy this up, square both sides and move y prime to one side. So I have y prime squared. If I square and multiply, then I need to have 1 minus c squared sine squared of x equals c squared. Okay, so I'm done now because I just need to say that, well, I integrate. So I divide by this term, take the square root and separate variables, and I get y minus y0 equals an integral of c divided by 1 minus c squared sine squared dx. So I leave the rest as an exercise for you. And the answer to this exercise will be, so now we really, up to this integral, we've solved for geodesics on the sphere. If we do that, we'll know how little x depends on little y, or little y depends on little x, and we want to visualize it in terms of the spheres in R3. We will go back to these Cartesian coordinates, capital X, capital Y, capital Z. And then we really will see, because we know how capital X, capital Y, capital Z depend on little x and y. So we'll see how, what is the dependence on capital X, capital Y, capital Z on X along the geodesic. And the answer is that that the geodesic on the sphere are great circles. On S2 are great circles. The intersections of sphere itself intersection of the sphere with itself, with planes which go for the origin. So here is one such great circle, and it arises as an intersection of a sphere with a plane. The slight subtlety with this example is following. If I get 2 points on my sphere, and I want to connect them by a geodesic, then I'll find this unique great circle, and this great circle geometrically will be an intersection of the sphere together with a plane, and that plane contains 3 points, the origin, A and B, so 3 points in our predefined plane. But now you need to decide which segment to take. You can take the shorter segment and you can take the longer segment. So one of them is really a true geodesic, a minimizer, and that's the shorter segment. And one of them, it's still a solution. So we have to be careful. The longer one, it's still a solution, a perfectly valid solution of the Euler-Lagrange equations, except it's not a minimizer. It's an analog of what a saddle point, if you remember what it is. What the saddle point would be, neither a minimum nor a maximum. The bigger problem arises, or maybe another type of problem arises, if, but maybe let me write that first down as a comment. So 2 segments of a circle connecting A, B. Shorter is the geodesic, longer is a saddle. to distinguish between the two, using calculus of variations, we will need the concept of second variation. Now, this is true unless it so happens that these points A and B are antipodal points. If they lie on opposite antipodes, north and south pole of the sphere, then there will exist infinitely many geodesics containing these points. You see, because there are infinitely many great circles connecting the antipodal points. You can take this great circle and you take AB are, if AB are antipodal, well, then there exist infinitely many geodesics between A and B. Okay, so for the sphere, which is a kind of the most familiar to us surface apart from the plane, if you know about basic Euclidean geometry, for the sphere, the first Euclid axiom appeared to be broken. The first Euclid axiom is that for any 2 points, there exists a unique line segment, and by line segment, one means geodesic, connecting these points. Well, it's apparently not true for the sphere, because if the 2 points are antipodal, then you don't have. So it was, the geometry of the sphere was long understood, but it was in 19th century still task, problem to construct examples of surfaces, if there are any, which satisfy the first 4 Euclid's axioms, but not the 5th. So I'm going to remind you what Euclid's axioms are. So Euclid's axioms in the original formulation referred to as plane, but as one does with axiomatics, one forgets what the motivation was. One takes the axioms and sees what are the concrete realization of this axiomatic. First axiom is there exists a unique line segment connecting 2 points. So let's say we take a plane and we take a sphere. On the plane, this holds. On the sphere, it doesn't. Second one is that every line segment can be extended indefinitely. So the first axiom, for instance, 2 points, there will be a line segment, and the second axiom tells us, well, we have this line segment, might as well carry on. Well, that holds both on the plane and on the sphere, because once we have a line segment of a circle, we can extend it to a circle. Third axiom is that given a center and the radius, there exists a unique circle. By a circle here, one means a set of equidistant points, equidistant from the center. Well, that holds on the plane, but it doesn't hold on the sphere. Because if the radius of the circle in question, somebody gives us a radius of the point on the sphere is a center, okay? But if the radius of a circle is far greater than the radius of the sphere, you will not find the circle on that sphere. Yes.
Here we're drawing a circle on the level surface of the sphere, or?
Yes, so what's a circle on the sphere? So there are these great circles and they geodesics, but now we're talking about any circle. So maybe I pick this point. So my definition of a circle is a set of all points which are equidistant from this point.
But not all points will lie on the sphere.
Well, no, they have to lie on the sphere.
Oh, so
yeah, so it's a circle on the sphere. Our universe for this, we're trying to realize these axioms either on R2 or the sphere. I mean, you can imagine drawing a circle on the sphere, and the circle has a center, but the radius of this circle cannot be too big because it'll go outside the sphere. So that's why the axiom doesn't. Fourth axiom, all right angles are equal. And that's an old axiom to state, but what would be simplified is given two right-angled triangles on the plane, you can take one and rotate it and translate it so that the right angles of this triangle and the first one will coincide. Well, I didn't talk too much. I didn't define angles on the sphere, but you can do it by tangency. It turns out that this one actually is okay on the sphere as well as the plane. And the fifth axiom, the parallel postulate, so it's this. Given a line L, a little L, and a point P not on L, there exists a unique line containing P but not intersecting L. Okay, so on the plane, let's say that here is our line L, and here is the point P not containing L. And this unique line which this fifth axiom asks about is this one, the parallel line. Well, this holds on the plane. But it doesn't hold on the sphere because all, if I give you a line which is this great circle and a point not on this great circle, then all great circles through your point will intersect the first great circle at 2 points. So a sphere only satisfies 2 of the Euclid axioms. Oh, the problem, which dates back to Euclid now itself, was to see whether this fifth axiom is independent on the first four. And the way to do it, the way to show independence, people tried showing that it's dependent, but this led to well, the proofs were wrong. Way to show that the fifth axiom is necessary, is independent on the first four, would be to construct a geometry with geodesics which satisfy the first four axioms, but not the fifth. Is there a geometry, for example, question mark, which satisfies this, but not this? And if you could find one, then you will have an example of non-Euclidean geometry with one axiom and so forth. But the sphere will not do the job. So what I'm going to do tomorrow is to start off again with my Romanian metric, but not for a sphere, for a different surface, and construct such a geometry, and in some detail, and it will be the hyperbolic geometry. We'll talk about the upper half plane model of hyperbolic geometry. That's all for today. So, guys, yes.
The second axiom, when we say indefinitely, we're ignoring that it comes back to its.
We are ignoring it, but we're saying that it can be so indefinite. Well, the sphere is compact, so and one can argue, what was indefinitely means, but it can be. The thing is, any segment can be extended uniquely to only one great circle. So I think it's fair to include that.
Okay, and the fifth axiom, I don't understand how it would intersect the parallel line at 2 points. It's parallel.
Well, if you have a sphere, so the analogon of a line is a great circle. So here is our L. Well, we need to pick a P, not on L. In fact, I wanted this L to be blue. Start again. That's my L. And I have some P, not on L. Well, is there a great circle, which is a line, containing P, but not intersecting L? No. Whatever other great circle I'm going to draw, maybe this one, will intersect this great circle.
Oh, wait, the great circle has to intersect the antipoles, the poles?
Well, for any great circle, there are, you see, my sphere doesn't have the antipodes. I could have told you what the antipodes are, but I didn't. I just picked a great circle. So this great circle has the poles with respect to this point and that point, right? And another way to rephrase it is that any two great circles on the sphere intersect. Now, how do you see that geometrically? Well, remember I told you that the great circles are intersections of the sphere with planes for the origin. So take two planes for the origin. Planes for the origin, each of them is a great circle. Planes for the origin intersect in a line. But if you have a line, that the line will intersect the sphere at two antipodal points. There are always two intersections. But the fifth axiom requires you to have no intersections. Okay?
So the contradiction to the fifth axiom, now this model gives us that there doesn't exist a parallel line.
There doesn't exist even one parallel line.
So is there another model where there exists two parallel lines? Because this contradicts also the fifth axiom.
Well, the geodesics are not unique. So if you start to take double covers, if you want to have exact two parallel lines, then it is, if you took a double cover plane, compute math. But the real deal, which we'll solve tomorrow, will be a geometry where there exists not two, but infinitely many parallel lines. So that's what happens in hyperbolic geometry. But we will honestly solve equations and derive. We'll see what these lines are. Okay. See you tomorrow.
Thank you.